previously looked at inverse functions, right? And you remember with inverse functions, does anybody remember like how you could tell if a function was the inverse of another function?
No. No line.
Huh?
Horizontal line test and the vertical line test.
That's how I can tell if it was a function.
Well, so if I have f of -1, f -1 of x, and f of
It would
x,
equal x.
how can I tell that they're functions of one another? I mean, inverse functions of one
Because if you plug one into the other, it would equal x.
Exactly.
How do you
Yeah,
remember
so if I do f
I
of
don't know.
f of -1,
No chance. I don't
Okay.
We're good at Jesse.
that equals x, and then vice versa, right? If I plug that one in the other one, I get that.
Yes.
Nice. All right. So we're going to talk about the inverse of a matrix today, and it's not quite the same as what you get. You don't get x, right? Because this is in matrix. Matrices are a little more complicated than that usually, but just to kind of give you a definition, the inverse of a square matrix. This is the definition of inverse of a square matrix is the matrix. The way we label it is a to the -1. You know, kind of the same sort of the way that we label a function as an inverse. That -1 looks like a -1 power on it, where a is an n by n matrix. And with this one, when you multiply them together, so a times a to the -1, or the inverse of a, equals the identity matrix, which we're going to label as I with a subscript n. And the order doesn't matter. Just like if you plug one function in the other, you always get x, whether you're plugging the inverse into the regular function or the regular function into the inverse. Same thing here. When you multiply, whatever order you multiply it in, you're still going to get that identity matrix. And so, by this definition, a to the -1 is the inverse of a. All right? Note this, though. It must be square in order to find the inverse, in order for it to have an inverse. It must be square. Now, did we talk about the identity matrix last time?
We
Yes.
barely did. We would.
It was right, yeah, we defined that. So yeah, it's just a matrix that looks like, you know, it's got ones, all ones here and zeros everywhere else. So that would be the identity matrix for a 3x3 matrix, okay? So let's do an example, just so we can kind of see that in action. Example 1, on page 532, and they just say show that B is the inverse of A. So they give us 2, and the first one is, figured it'd be a good idea to go through this because you guys, I'm sure, haven't thought about matrices at all over the break. So let's do some multiplication. Okay, so we've got to multiply these together, and if they're inverses of one another, what are we expecting?
To get an identity matrix.
We're expecting something that looks like this, right? So let's see if that's true. Who can tell me how I get my, if this is a 2x2 matrix and this is a 2x2 matrix, can we multiply them together?
Yes.
Yes.
What are we looking at to make sure that we can, to verify we can multiply them?
The two middle numbers
The
make
two
it
middle
the
numbers,
same.
right? So if these numbers are the same, then we know that they can be multiplied together. And what is going to be the size of the resulting matrix?
2 by 2.
It's going to be the outer numbers, right? So if these had been different, it's whatever the outer numbers are.
The M and P.
So we're going to have a 2x2. We do know that. We'll just write that down here. And then remember the way that we do this is it's which number is first? Is it the row or the column that appears first when we're given the size of the matrix? The row and then the column?
Yeah.
All right, and so how do we multiply?
U times like the first You take the column by the first number.
We take this row and multiply by that column. Is that right?
I did it differently in all of my problems, but I think.
Wait, we did what?
It's like you got a new way to do it, Diego? It's like, I decided it would be better if we
Wait,
did
I'm
it
gonna
like
do it
this.
on the bucket.
Mr. Walker, what did you say?
Is it the row times the column? Or is it the column times the row for that first term? Do you guys remember? It's the row times the column, right? So what we're going to do, let me give us a little more room. So we're going to take this row right here and multiply it by this column. So negative 1 times 1 is negative 1 plus 2 times 1, which is 2. So that'll be our first term, right? And then we do row, I'm sorry, I'm forgetting. Claire did do this. She was doing some karate here. So let me give her credit for that. So then negative 1 times negative 1. Wait a minute. What did I do? I did something. Did I do that right? I did it right.
Even Mr.
Negative
Walker.
1. Yeah?
Even Mr. Walker.
Yeah, exactly. Negative 1. So now we're doing this one times this column.
Are you
Wait,
sure?
wait,
Are
wait
you
a
sure
minute.
about that?
Wait a minute.
Look.
I haven't thought about matrices either. Right. So it's this times this, and then this times this. Okay.
Yes,
here we
it's
go.
the first.
So I'm going to do this times this. Let me do this times this column, and then this top row times that column. So now we're going to put that right here. All right, so negative 1 times negative 2 is a positive 2, and 2 times a negative 1 is negative 2. Sound good to everybody? Okay.
Yeah, that's great.
And this is also good because it's working out like we want it to work out, right? So now we have a row times this column is going to be this term. So we got a negative 1 times plus a 1. So negative 1 times 1 and 1 times 1. And then finally, this row times this column. So negative 1 times negative 2 is a positive 2 minus 1. Did everybody follow that? As I'm sort of pointing and saying this one to this one, did you know how we did
Wait,
that?
how'd you get 2 minus 2? I got lost in that.
So that was this row, that was this row, negative 1 and 2 times this column. So negative 1 times negative 2 is a positive 2, and 2 times a negative 1 is a negative 2. Got that?
Yes.
Okay. And so, if we do the addition here, sure enough, we get 1, 0, 0, 1. Right? So we get the identity matrix. Now, are we done?
I wish.
You wish, right? In order for this to truly be an inverse, we should be able to flip the order of these guys and also get the identity matrix. So let's do that real quick. 1, negative 2, 1, negative 1, times negative 1, 2, negative 1, 1. All right. And so we're gonna do this in our heads, right? 1 times negative 1 is negative 1 plus negative 2 times a negative 1 is a positive 2. So negative 1 plus a positive 2 is going to be 1. Negative 1 times 2 is 2. Negative 2 times negative 1 is negative 2. So sure enough, we get a 0 here. 1 times a negative 1 is negative 1. And then negative 1 times, wait a minute. Yeah, sorry, we want a 0 there. It's like, wait a minute, it's turned out to be a 0. 1 times a negative 1 is negative 1, plus a negative 1 times a negative 1, which is a positive 1. So negative 1 plus 1 is going to be 0. And then finally, 1 times 2 is 2, and negative 1 times 1 is negative 1, so 2 minus 1 is 1. So we get the identity matrix regardless of the order that we multiply these in, and so these are, in fact, inverses of one another. Are matrices confusing? Yes. Right? There's just a lot of places that you can make a dumb error, right? And I'm like you guys, I'm a little out of practice right now. But is everybody clear on that? You guys see how we did that? All right. How do we, excuse me, if we look at example 2 in this same section, here we're trying to find the inverse using variables. So we can think about it like this. trying to figure out what, if I'm trying to find the inverse of A, right, then it's what matrix can I multiply A by, so we're just going to say some matrix X, right, so that I get the identity matrix. And sometimes you'll see the identity matrix written with a subscript here that identifies the size of the identity matrix, but sometimes you'll just see it as I. So either of those are acceptable. So for this one here, and I don't really want to work all this out because I don't want to take the time to do that. But if we say A, if they give us A as being 1, 4, negative 1, and negative 3, 1, 4, negative 1, negative 3. And we're trying to find the inverse of that, then we're looking for something that's going to give us this, right? That identity matrix. And so for this guy here, they use X, but they do like X11 and X12, right?
That's what they did in the examples, right?
To me, what'd you say?
That's how they did it, and like when they defined it, they did like in points, it was like A11, A12.
Yeah, you could do that. You could do that. You could do it with any variable that you want to, right? You could just say A, B, C, D. To me, it's kind of more work if you got to put little 1-1s and 1-2s and all that kind of stuff. But the point is, when you multiply these out, you're going to get something that that's going to have all those variables in it, right? And you just have to determine what combination of those variables is going to give me. You're going to end up with a system of linear equations that you're going to have to solve. So let's just do one, all right? So if I do this, 1 times A is A. 1 times A is A plus 4C, right? And then this one here is 1 times B is B plus 4D. Here I have negative A minus 3C. And here I have negative B minus 3D. Does that look right?
Mm-hmm.
And so notice when we do this, we can say we've got a system of equations based on these two linear equations. So we can say that A plus 4C equals 1, right? If it's going to be the identity matrix that results from this. And then A minus 3C equals 0. And so then we could solve that and say here, we could just say A equals 3C. Whoops. Wanted to use substitution. A equals 3C is what we convert this bottom equation to, and so then we take that and plug it back in here, and so 3C plus 4C equals 1, and so 7C equals 1, so C equals 1/7. Is that what they got? It's not. I knew that. What did I do wrong, guys? A
You got the A plus 4C equals 1.
Oh, here's what I did wrong. This is supposed to be negative A. Is that right?
Yeah.
That's supposed to be negative A. So that's a negative. So then A equals negative 3C. Negative 3C. If you put a negative 3C in here, we get C equals 1. So that gives us C, and then we can plug C back into here, and we can say then A has to equal negative 3. So we've got the 3, negative 3, and 1, and then we can do the same thing for the other system of linear equations and see that B has to be negative 4 and D has to be 1. And of course we can check this by now taking these and multiplying the two together, and we should get this, and then we can reverse it, and we should get that again. Did everybody follow that?
Mm-hmm.
So you can use whatever variables you want. If you want to do x11 and x12, I don't know. It just seems like it's more work to me than have to keep up with that. Any questions? So So that's the longer method. We're actually going to see an easier way to do that. Now that I've taught you the longer method, it wasted your time.
So if we have a quiz on this, do you want us to use the longer method, or are we allowed to use the shorter method that we're about to?
Honestly, we're going through so much material that we'll probably just use the shorter method. So, but I'm sure you'll have some homework problems where you use the longer method. So, and the longer method always works, right? I probably won't even care. I'll just say find the inverse. So you can use whichever method you want. So you could do, instead do what they call a double augmented matrix and apply Gauss-Jordan elimination, which is where you put it in reduced row echelon form. And if we look at page 534, you kind of see an example of that where they so they put the two together. So you see how, excuse me, they had this -1, 1, 4, -1, and -3. And so just like we would put our line here, on the other side of this, normally we're accustomed to seeing just one column of numbers there, but you put 2 columns of numbers to show the identity matrix. And then you start doing row operations to basically turn this side into 1, 1, 0, 0, right? So you use all of our row operations that we normally use to do that. And what happens is as you apply those row operations, this side over here ends up turning into, where is it? -3, -4, 1, 1. So we end up getting on this side what the inverse of the matrix is as we do those row operations. So like for this one, like the first thing we might do here is we would combine, we'd say we're going to, we want to get a 0 down here, so we're going to add row 1 and row 2 together. Row 1 plus row 2, and that's what we're going to put right here. Let me do it like that. And so when we do that, we get 1, 4, 1, 0 still on the top, and by adding all of them together, we get a 0 here. We actually go ahead and get a 1 there, and then we get a 1 down here, and we get a 1 down there. And so we want to get a 0 up here, and so we would say -4 times row 2 plus row 1, and we get 1 here, we get a 0 here, 0, 1, and then -4 times row 2, -4 plus a 1 is going to give us a -3 here, and -4 plus a 0 is going to give us a -4 here. And so we get, when we add we don't add those, so that just stays 1, 1. Yeah, so that's it. That's the only 2 operations we have to do.
I don't understand the last part. So you multiply -4 times the second row?
Yeah, so -4 times this row, and then I added it to row 1 and replaced row 1 with that. Does that make sense? So -4 times 0 is 0, 0 plus 1 is 1, right? -4 times 1 is -4, plus 4 is 0. -4 plus 1 is -3, and -4 plus 0 is -4. So I changed the bottom row stayed the same, I changed the top row. Yes?
Can you go over just one time the R1 plus R2? Just like you
Yeah.
So you just add 1 and 4 and -1 and -3, and then you just push them into that.
Say that one.
I'm confused how you did the first step.
The first step, this one here?
I just need a refresher.
Yeah, so I wrote it down here so that we would realize the row that we were affecting was the second row.
Yeah.
So we were replacing the second row with the 2 rows added together.
Yes.
And the reason I did that is because I was trying to get a zero term here. It was
Yes.
already kind of set up where that would give me a zero term.
Yes.
So I just did 1 plus a negative 1 is 0.
Mm-hmm.
4 minus 3 is 1.
Okay.
1 plus 0 is 1. 0 plus 1 is 1.
Okay, cool.
Make sense?
Yeah.
Any other questions about that? I mean, I have to sort of move through it quickly when we do it because it's such a long process, you know. This is why we only covered one section. But like I said, if you do this, then the inverse of it will appear, right? Will be what's on the right side here will end up turning into the inverse of it. So they've got the steps listed down for that at the bottom of page 534. Just for time's sake, I'm not going to write that down. But it just shows that it just says to do what we just did, right? It has to be a square matrix. That you can only find the inverse of a square matrix, so that's important. It's got to be square in order to find the inverse. And so you write down a matrix that, you write down the original matrix here, and you write down the identity matrix on the other side. Write it down as a double augmented matrix. Remember when we say augmented, that just means it has the line here. It has, the items that are on the right side here. So you write it down like that, and then you reduce A to I using those elementary row operations that we learned about. So you basically turn this into that. And if it's not possible, there may be instances where it's not possible to do that because the way things add up and all, some of these guys, multiple ones may turn into 0, and once that happens, then you're not going to be able to go any further. So it's possible that it won't have an inverse. But if you can find the inverse, then you will be able to reduce this down to reduced row echelon form. And then, like I said, you check your work by then multiplying this by this and making sure that you get the identity matrix. Example 3, for example, gives you one that is not, you can't find the inverse for. Was it example 3? Wait a minute, it's the bottom of the page. Sorry. So example 3 is a bigger one. It's a 3 by 3 matrix, so we know we can attempt it because it is a square matrix, and so they're able to find the inverse there. But down at the bottom of the page, that matrix there is not invertible. And you'll know that it's not invertible because, see, as they're doing the row operations, what happens on the very bottom there? You get a row of all zeros. And once you get that row of all zeros, then you're in trouble. You're never going to make that left side be the identity matrix once that happens. All right, any questions about finding the inverse? Nope. All right. There is a special method for finding the inverse for a 2 by 2 matrix, and they have that formula there. If you want to remember that formula and maybe write it down on your note card for the test, and that's an option to use that for finding the inverse. And it just, like I said, this is for 2 by 2 matrices only. If A equals A, B, C, D, and then if and only if AD minus BC does not equal 0, A negative 1, or the inverse of A equals 1 over AD minus BC times D minus B C A. So that using that formula there will give you the inverse. And remember, this is just a constant. And so when you multiply a matrix by a constant, you just multiply all of the terms in here by this constant, right? If we had 3 times this, then the resulting matrix would just be 3D minus 3B, 3C, 3A. So it's just a formula for you to use. You quickly find it with a 2x2 matrix. And this denominator here is going to come back. We call this denominator the determinant. So it has a special function and a special name, and we'll see that in the next chapter. So who cares? Why do we need to find the inverse of a matrix? Anybody know?
No.
You weren't pondering that deep question over the break?
I wasn't. Sorry.
The reason why is because with matrices we don't have any way to divide, right? We taught you guys how to add and subtract and to multiply, but there's no way to divide. And so what if I want to divide by another matrix? Well, the way that I would do that is I would multiply by the inverse of that matrix, right? Just like if we have 3 and I want to divide 3 by 2, right? That's the same as multiplying 3 times 1/2, right? And so this 1/2 is the inverse of 2. And so it's the same way with, or the reciprocal of 2. It's the same way with matrices. If I want to divide, then what I do is I can find the inverse of the matrix that I'm dividing by first, and then I can multiply the 2 together. Yes?
So it's kind of like how we do fractions, like when we divide fractions, you don't really divide them, you just multiply them.
Yeah, by the reciprocal, right? So it's the same idea here. That's why inverses are important. All right. Let's see. Represented by AX has a unique solution. So there's let's see, I noted that example 5. So the point with example 5, if you look at that in the book, it says, use an inverse matrix to solve the system. And if you write that system down, system of equations, 2, 3, 2, 3, 3, 4, 1, 1, 1. I'm just taking the coefficients of all the variables in our system of equations, right? And we're trying to solve this system of equations. We can think of that, we can write it like this. This matrix here multiplied by this matrix, which has all of my variables in it, equals everything that's on the other side of the equal sign here, -1, 1, and -2. And so, if we think of this as A, and this is X, and this is B, right, then we're saying that A, X equals B. And if I want to solve for X and find the values of X, then I could basically divide both sides by A is normally how we would do it, right? But we don't have this concept of division in when we work with matrices, and so we would say that X is equal to the inverse of A times B. Right, so we could perform this operation here, and it would give us the values for those variables. So if we found the inverse of A, which we now know how to do, right? We can use I'm not going to do it, but we can do the whole 2, 3, 2, 3, 3, 4, 1, 1, 1, right? And then say 1, 0, 0, 0, 1, 0, 0, 0, 1, and convert this into reduced row echelon form. And then over here we would end up having the inverse matrix. And so when we did that, we would see that A inverse equals negative 1, 6, 1, 0, negative 2, and 0, 1, negative 3. And so now I can take this guy here and I can multiply it times B. So if I took this and I multiplied it times B, can I multiply those together? What's the size of this matrix?
That's
3 by 3. What's the size of this one?
1 by 3. No, 3 by 1.
Is it 1 by 3 or 3 by 1?
I don't know. 3 by 1 because the two inside ones have to be the same to multiply. So 3 by 1.
So these, we have 3 rows and 1 column, right? So that means we can multiply these together. The resulting matrix is going to be a 3 by 1 matrix, right? It's going to look like that. And if we do that multiplication, we get 2, negative 1, negative 2. So that means that x equals 2, y equals negative 1, and z equals negative 2. All right? So I don't want to do all the multiplication all just because it's time consuming, but do you guys see how I did that? Do you understand the steps? And remember, we started with a system of linear equations, right? We started with something that was 2x plus 3y plus z equals negative 1, right? And 3x plus 3y plus z equals 1. 2x plus 4y plus z equals negative 2. So we can solve those systems, a system of linear equations like that, by going through these steps. Any questions? Just another set of tools in your arsenal for solving these types of problems. All right, I promised you guys we're going to talk about determinants, so let's do that. This will move us into section 7.7. No questions? You guys are kind of looking down, and some of you are still writing. Oh no, we got the tomahawk chop going on over here. Was that a tomahawk?
No.
Okay. All right. I'm losing you. I'm gonna have to spice things up a little bit, right? Let's see. See if I can talk a little more excitedly about determinants. What if I did the rest of the lecture in an English accent? Would that be better?
No. Please do.
Did you guys have to use accents in the play?
Oh no, we did
Huh?
that. We did talk in an English accent for a
Did
while.
you?
Backstage.
That's
all the
awesome.
time. We don't know why.
We did it all the time.
Yes, it was quite
But you
fun.
didn't actually do it in the play?
No, we didn't.
Oh.
Evan did it.
Evan did.
Well, but it takes place in France.
It does take place in France, so it makes
So the
sense.
words wouldn't sound right.
Everything sounds better with an English accent.
I think you should speak in an English accent.
Okay. I'm so excited to share with you guys about determinants. I know you're going to love
Mr.
it.
Walker, if I may, you strike me as more of an Australian man.
His
Your accent
problem
reminds me more of an Australian.
I can't really do an Australian accent, so it just sort of combines together into my
really
English
more like
accent.
a country British accent.
Have you seen Despicable Me?
Yes.
You ever seen that? Okay, so the accent that Steve Carell did in Despicable Me is really not an accent of anything. He just kind of mixed a bunch of stuff together and came up with Gru's accent. So that's kind of what I am. I'm a master of mixing accents together.
Really?
Oh, it's quite lovely.
All right. So let's do a system of linear equations. If we have something like this, A1, So a1x plus b1y equals c1. And then we had a second linear equation that looked like this. All right, so just linear equations. How do we know it's a linear equation? How do we know it is a linear equation? You're only going to answer me if I speak English. How do I know that? Why is it a line? A linear equation just means it's the equation for a line. Huh?
Because it has x and y.
It only has two variables. It just has x and y, right? So, I mean,
straightforward.
we're looking at all that. Yeah, come on, guys. It's so easy. But because it's x and y. All right? And so we could solve for y. If we solve for y, and I'm sorry, you're copying this down and you probably don't need to. But let me just say this. If we solve for y, this is what we would get. We would get a1 c2 minus a2 c1 over a1 b2 minus a2 b1. All right? Just trust me. We're not going to do that. But that's what you would get if you solve for y. And we're algebra maestros, so we can do that if we were called upon to do something like that. What if I asked you to solve for x? Well, if you solve for x, you would get c1 b2 minus c2 b1 over a1 b2 minus a2 b1. All right, so do you notice anything about those two solutions? What's similar about the two?
The bottom is the same, the top is just, the top is the only part that's different.
Yeah, you already said the important thing. The bottom's the same, right? The point is, whenever you solve them, you get the same denominator for both y and for x. And so that's where we get the idea of the determinant from. That's how they came up with this concept of determinant. So let me define a determinant definition of determinant of a 2x2 matrix. Right, because that's the size matrix we would have if we were solving two linear equations. The determinant of the matrix A equals A1, B1, A2, B2 is, there's multiple ways that you can write this, determinant of A. That's one way that you may see the determinant written. You can see it written like this. So it looks like absolute value of A.
But it's not.
It's not. If A is a matrix, then those, what looks to be absolute value lines means determinant. All right? So the determinant of A is one way to write it, or you can write it like this. You just rewrite the matrix, but instead of using the square brackets like we normally use to identify a matrix, you use those absolute value lines there. Or you could write it as A1 B2 minus A2 B1, which is the denominator that we have over there when we solve for x and y. Right? So all of those are ways to represent the determinant. And that's how we define the determinant. Notice what we're doing here. If we have this matrix here, and you're told to find the determinant of that matrix, then we basically multiply these. It's like cross multiplication, what it kind of looks like, but you're subtracting. So you multiply the A1 and the B2, and then you multiply this way, and you subtract that out. So you take the difference of the two when you cross multiply what's inside the matrix. All right, that's the determinant. Any questions about that? All right. So if you look on page 542, they have a bunch of examples, a bunch of opportunities us to first define the determinant. And so just to kind of show you how we might write this down, I'm going to say, the first one I'm going to say, find that. right? So that means find the determinant of A. And so we just cross multiply and we say 2 times 2. Let me write A down just so you guys can see it. So we'll have it here on the board. I'm going to write each of these down actually. A equals 2, 1, negative 3, 2. B equals 2, 1, 4, 2. And C equals 0, 2, 3 halves, and 4. All right, so the first one, I say, hey, find this. And so you go 2 times 2 minus 1 times negative 3, right, which equals 4 plus 3 equals 7. So the determinant of the first one is 7. So the second time, I don't say find this, I say find this. But you look at that and you go, oh, he's just asking for the determinant of B, right? So if I write it like that, I want you to find the determinant. So that's 2 times 2, again, minus 4 times 1. So that's going to be 4 minus 4, so this is going to be 0. And then on the last one, I say, find this. And again, that simply means find the determinant of this matrix, C. So we multiply them together. This 0 times 4 is just going to be 4 minus 2 times 3 halves is going to be 4 minus 3. What did I do wrong?
0.
Oh, there's a 0 there. I'm sorry. Yeah, 0. I was like expecting the negative number. 0 minus 3, so that's going to equal negative 3. And so they give you these 4 examples just to show you that the determinant can be a positive number, it can be a 0, or it can be a negative number. There's really not any rule. Doesn't have to always be positive or something like that. That's a pretty straightforward concept, right? Just something you have to remember, but everybody understand that? Okay? All right, so let's talk about minors and cofactors. Oh, well, let me make this note. If you have this, what if you have this? A equals negative 2. All right, you can have a 1 by 1 matrix. And so if I tell you to find the determinant of A, and it's a 1 by 1 matrix, then the answer is just whatever the value of the matrix is, right? Yeah, exactly. Mind blowing.
What if it's just a 1 by 2 matrix? Would you just do those two?
It can't be. It's got to be. It's got to be square.
Okay.
So that wouldn't be an option. All right. So we know how to find it for a 2 by 2, but what if we want to find the determinant of a 3 by 3 matrix? We don't really have a way to do that yet, and so I'm going to have to define minors and cofactors in order to help you find the determinant of a matrix that's greater than a 2 by 2. So, where am I going to put this? I'll put this over here. If A is a square matrix, then the minor, to define that term, and we're going to write that as capital M, little I, little j, subscript there. The minor of the entry, the minor Lij of the entry Aij is the, this is hard to write down, the determinant of the matrix obtained by deleting the ith row and the jth column of A. The cofactor, the other concept we need to be familiar with, the cofactor C, is that a little c or a big C?
It's a big C.
Is it the cofactor Cij of entry Aij is Cij equals -1 raised to the power of I plus j times m ij. And all that means is that C is going to be, it's going to have the same absolute value of m, but the sign may flip on it, depending on what row, which row and which column you're in. So it's a lot harder to write that down than it is to just sort of show you the example. So let's see, where do I want to go? Page 543. So they give us an example 2. They say A is equal to 0, 3, 4, 2, -1, 0, and 1, 2, 1. So they give us this matrix, and they want us to find all of the minors and cofactors, but let's just start with M11, all right? So M11, that's going to correspond to entry A11, which is this entry right here, all right? That's A11. And so what you do when you're finding this one is you basically, wherever the entry is that you're focused on, you cross out the row that corresponds to that entry, and you cross out the column that corresponds to that entry. Okay? And so then, Mij, or M11 in this case, is just going to be the determinant that results from this. So if we find the determinant of that, we get -1 times 1, which is -1, right? Minus 0, so it's just going to be -1 for the determinant of that. That's M11.
So it's the determinant of what?
It's the determinant of this matrix that we formed by crossing out this row and column.
Okay.
So it's -1 times 1 minus 0 times 2.
It's the determinant of the matrix -1, 2, 0, 1. Right?
Yeah, exactly. This matrix right here, -1, 0, 2, 1. Right?
What does that accomplish?
Oh, you'll see.
I'm trusting you.
Right now I'm just showing you the steps.
Okay,
Right?
okay.
Alright, so we're just trying to find M, the minor, that corresponds to that entry. Alright? And so what is the cofactor that corresponds to that entry? So C11, like we said here, is going to be -1 to the power of I plus j, which in our case is just 1, 1, so 1 plus 1, times whatever we found for the minor, which is M11, which we determined was -1. And all this is doing is it's going to tell us if C is going to have the same sign as M or if it's going to have a different sign. So -1 raised to the 1 plus 1 is -1 squared, which means this becomes a positive 1. So C in this case is going to have the same sign as M does. Yes?
Where's the 1 plus 1 from?
From this. That we're at entry 1, 1.
Okay, so if it was like entry 1, 2, 1, 2, you do 1
We do
plus
1
2.
plus 2.
Okay.
So then it would be a negative. Then the sign would flip-flop. Okay? So you do that for each of these guys. Let's do L12 just to give you one more example of that so that it'll make a little more sense. So if we do L12, now I'll just rewrite the matrix again. A equals 0, a little bit bigger. A equals 0, 3, 4, 2, -1, 0, 1, 2, 1. Right? So this, now we're interested in this entry, right? This entry right here is A12. Everybody agree with that?
Yeah.
A, row 1, column 2. All right? So if this is the entry that we're interested in, we cross out this row and we cross out this column. Okay? And again, when we do that, we have a 2 by 2 matrix that is still visible. So the 2 by 2 matrix is 3, 4, 2, 1. If I just take the numbers that haven't been crossed out. Everybody see that? Make sense? So now I take the determinant of that, which is going to be 3 times 1 is 3, minus 4 times 2, which is 8. So 3 minus 8 is -5. Right? And now, because 1 plus 2 is a negative number, 1 plus 2 is an odd number, then C12 equals -1, 1 plus 2, right? That's the row and the column that we're on, times whatever M was, which was -5, means that now this -1 stays a -1 because we're raising it to the third power. And so that's going to flip the sign on my -5, so my answer for C in this case is going to be the opposite sign of what M was. Okay? And so we could find that for each of these guys, and if we found it, they've got them listed at the bottom there. We've got what M1, M2, M13, and all that stuff is. And then they've got the corresponding C values, the cofactors, at the bottom. But this is the way it's always going to work out with a square matrix. And you can see this at the top right of the page. If we have a 3 by 3 matrix, this is the signs for cofactors. If you have a 3 by 3 matrix, the cofactors is going to be, it's always going to start off with plus at the top, and then the sign is going to alternate
So
all the way down like that.
basically all you need to know is for like, if it's like an odd number, it's just going to be the opposite. That's going to be the same sign. But if it's an even number, it's going to be the opposite sign for like the first and third rows.
Well, if it's an even number, the sign's going to be the same. Now, when we have 1 plus 1, if this comes out to be an even number.
Oh, I meant like if it's like 1 plus 2, that 2 is even, so the sign's going to change.
Well,
Is that what's the case, or?
the sign will change if it's 1 plus 2, but what about when you get down here where your first number is, instead of being a 1, your first number is a 2, because you're on row 2 now? Now it's going to be 2 plus 1, which is going to be odd, so the sign will stay the same, 2 plus 2.
Yeah.
Right?
But for like the first, like it says in the 3 by 3 matrix, the first row, that's the case for that first row.
For the first row, yeah.
But then it's different, it's switched for this.
Yeah. So you could just remember this. You could just remember that
Yeah.
whatever the size of the matrix is, it always starts off with a plus in the top left corner, and then alternates as you go across, and then it alternates when you jump down to the next row, and alternates as you go across.
Okay.
So you can think of it like that. Again, for time's sake, I'm not really going to be able to give you guys anything bigger than a 3 by 3. You know, so as long as you know how to work the 3 by 3, you should be fine. All right, so this is why we need to know that concept, because again, we don't have any way right now of finding the determinant of a matrix, of a square matrix that's bigger than a 2 by 2. All right, so that's why we learned these concepts here. So how do I do that? I'm going to write this. I'm just going to move this up to here. Equals A1, B2, minus A2, B1. Write that down there. And we'll say the determinant of a square matrix. If A is a square matrix of 2 by 2 or greater. So this will work on any square matrix that's bigger than a 1 by 1. Then the determinant of A is the sum of entries of, this is important, of any row or column. You can even do it with columns. Multiplied by, let's see, let me put this out there. Multiplied by I'm so glad that I learned about knee pads when snowboarding. Because since I snowboarded last week, I would not be able to do this right now if I had worn knee pads while I was doing it. Multiplied by the respective cofactors. For example, for first row, the determinant of A is equal to A11 times C11 plus A12 times C12 plus dot 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 plus A1. Change these ones to look like that so you make sure you know these are ones. A1N times C1. And we call this called expanding by cofactors.
And so this would get you the determinant for the entire matrix.
For the
correct?
entire matrix.
So if you found the cofactors for like that first row in that last matrix we did of like the 0, 2, 1, you found the cofactors, which on the bottom of the page are -1, 5, and 4.
Right.
And then you did all of that. You plugged it into that equation.
Yep.
What you would get would be the determinant for the whole.
For the whole matrix. And you can do that with any row.
So any row, and you get the same determinant.
Yep.
Okay.
That's exactly right. Yep. So if we think about that for a moment, or you could do it with any column, right? You could pick a column and you could do that. So if we think about it, which row or column are we going to pick in our matrix? What makes the most sense? If we're multiplying C by whatever the entry is in that slot in the row or the column, it's going to make the most sense to pick a row or a column that has the most zeros in it. Because all these terms that are multiplied by a 0 are just going to go away, right? So, like Hayden said, for this one here, where we had 0, 2, 1, what is it right here?
It was
3, -2.
Yeah, 3, -1, 2,
1, 2,
401.
4, 0, 1. All right. So for this one, in order to find the determinant, you're either going to want to use this row or this column, because it has a 0 in it, right? Or you could use this row or this column, because it's got a 0 in it. If you happen to have a row or a column that's got 2 zeros, that's the one you should pick, right? If this was a 0 right here, then this would be the column that we definitely want to use to get the determinant, because you only really have to focus on one term there. Does that make sense to everybody? So let's just do this one here, just for grins, right? Just for kicks. So if we did this one, we're focusing on row 1. So all we actually need to find is what is find out C12 right here. So we would cross this out, right? And we would say the resulting matrix is 3, 4, 2, 1. This is actually the same matrix that we did a moment ago when we were finding M12. So we determined that M12 equals -5. And then when we found C12, we saw that it flipped the sign, right? And so C12 is a +5. And so then when we're plugging it in down here, that means that the determinant, since this is A, the determinant of A is just equal to this A12, which is 2, times C12, which is 5. So the determinant for this matrix is 10. So all we had to do was focus on that one row to figure out the determinant for the matrix. If we picked another row, it would have been more work for us, and we would have gotten the same answer. Or if we picked another column, we would have gotten the same answer. Do you guys believe me?
Yep.
We would have gotten the same answer. Okay, good. You will. Trust me. Do we need to try it? Do I need to prove that? You guys good? Because this is the last concept of this chapter. So I want to make sure everybody got that. You guys understand what we just did? Do I need to go through it one more time? All right, let's do it one more time. All right, let's do it on a different one just to check it out. So this is our matrix. That's a 2 right there. 0, 2, -1, 0. So we'll choose another row or column this time. So that it'll be a little bit harder for us. But let's say we want to use this row right here. All right. So if that's the row that I'm focusing on, we're going to have 4, 0, 1 on it. I'm going to cross this out so that I see the resulting matrix because I'm focusing. Wait a minute. Why did I do that? I didn't mean to do that. 0, 2, 1. 0, 2, 1. That's a 0. What I'm crossing out actually is I'm focusing on this entry right here. So I'm going to cross this out. And I'm going to figure out what. So that entry there is A13. Right? No, A31. Row 3, column 1. And so that entry is 4, all right? I'm doing this whole row here, so A32 is going to be 0, and A33 is going to equal 1. All right, so what are my corresponding ELMs values, my minors for these guys? ELM31 is equal to this. The determinant that I get from this, so 2, which 2 times 2 is 4, minus a -1 is 4 plus 1, so that's going to be 5.
No.
No?
Because -1 times 0 is 0, right?
Oh, you're right. Why do I keep doing that?
It's just 4.
It's just 4. All right, thank you. So it's that. And then, what about, well, we'll just go ahead and figure out C for this. C31 is equal to, is our sign going to flip or stay the same on this one? Remember our little, looks like this, plus, minus, plus, minus, plus, minus, plus, minus, plus. So the sign stays the same for that one, right? Everybody follow that? All right. So now let's do A32. This is so hard with crossing it out. 0, 3, 4, 2, -1. I'm just rewriting it. 0, 2, 1. We're focusing on this entry, so I'm crossing these out this time. But do I even need to do that?
No,
I don't even need to do that because I'm going to multiply it by 0. So why did I do that? I was making a point. Yeah, that was it. 4, 0, 1, 2, -1. So we're going to focus on this one here. We're focusing on entry 1 now. So our resulting matrix is 0. The determinant here is 0 times -1, which is 0 minus a 6, right? So ELM
it will just be 6 because it doesn't change.
Equals 6, and it doesn't change, so C3 equals 6 as well. All right, did I lose anybody on finding the minor and the cofactor?
No. And then you just do.
So then when we just take each of these guys, you use this formula here, and we say A is equal to A11, or in our case it's A31, which is 4, times C11, which is 4, right? Plus 0 times whatever, right? Plus 1 times
6.
Didn't work out, did it? 1 times 6. 1 times 6. All right, so that gave us. What did I do wrong? do something wrong? 4. Yeah, because this is going to give us 16 plus 6, which equals 22. That's what I get for changing the problem on the fly.
Yeah.
Yeah. Huh. I definitely got the right thing. Well, I changed this one.
If you change the 0 back, I think it might have been 22.
Yeah, but still, it should have worked. All right, now I'll have to think about that one separately. I don't have time to figure out where my mistake was there. But the important thing was that you followed these steps, right? So you got that down. All right, cool. I wonder if it has to do with the fact that when I added the 0, maybe I made it where it didn't have an inverse, and could that have been related to it? I don't know. I'm not sure. I'll just have to rework that. I'll go back and watch the tape and see what I did wrong there. Okay, so that's the end of that section. Let's look at the next section very quickly. It is, though, like I said, the smartest thing for you to do is to pick the column or the row that has the most zeros in it. That'll be easiest for you. All right, so these are two really simple concepts that I just want to make sure you guys understand. This last section here, it allows you to find the area of a triangle using a matrix. So that's kind of cool. So the area of a triangle, if we're given 3 vertices of a triangle, you guys comfortable with me putting triangle there? Abbreviating that kind of thing. So the vertices are x1, y1, x2, y2, and then x3, y3. Then the area is area equals plus or minus 1/2. Whoops. X1, x2, x3, y1, y2, y3, 1, 1, 1. Where symbol plus minus allows you to choose the sign to get positive area. So basically what we're doing is we're finding, if we have our points given like this, right, then we create a matrix that looks like this based on these points, find the determinant of this matrix, right, and then we multiply it by positive half or negative half, depending on, if this is a negative number, if your determinant's a negative number, then you're going to multiply it by a negative half. If it's a positive number, you multiply it by a positive half. And we do that because area has to be a positive number, right? So it just allows you to pick the sign that will give you a positive area. So they have an example in the book where they give us these points, 1, 0, and 2, 2, and then 4, 3. So these are just the vertices on our coordinate plane that form a triangle. And so what we're going to do is we're going to construct a matrix that is based on these points. So we take all of the x's, 1, 2, 4, and write them like that. Then we take all of the y's, 0, 2, 3, and then we write all 1's down there. And so that's what we're finding the determinant of. And so we would use this row here, right? Would be an easy one for us to use. And if we found the determinant of that, since we're masters at that now, let's just try this one. Let's give you one more practice on that. So we're A11 is 1, and we're only interested in A11 and A13, right? And which is also 1. Everybody agree? All right. Let's see if we can find out what M11 would be. So we're going to just try to imagine it in our minds this time, so I don't have to actually draw a line through it. So I'm drawing a line. I'm interested in this entry, so I'm drawing a line through this, and this leaves me this resultant matrix here. So 2 times 1 is 2 minus 3, so it's going to be -1 for M11. And so C11 is going to have, if we remember, it starts with a plus in the top left of our matrix. In other words, the sign doesn't flip. So C is going to be the same sign. Okay? Don't have to worry about this middle term, because this is going to go away since there's a 0 there. So let's think about A13. M13, that means we're going to cross this column out, we're going to cross this row out. So we've got this matrix down here, right? So 2 times 3 is 6, minus 8, so that's going to be a -2. And because of its position, again, the sign is not going to change because it'd be plus, minus, plus. So the sign stays the same. And so C is also going to be a -2. So the determinant for this guy would be, if this is A, we'll just say this is A, then the determinant of A is going to be 1 times -1 plus 1 times -2. So that's just going to be -3. Is that what they got? Yep. And so then the area of our triangle, since we got a negative determinant, we're going to pick a negative sign in the front here, so that our final answer is positive. So -½ times -3 tells us that our area is going to be 3/2. 3/2 square units, since they didn't give us any units to start with. Okay? Easy enough? It's really simple. This last chapter is really simple. As long as you got down finding determinants. One final question. Let's say they gave us 3 points. Just like we had here, right? But let's say our 3 points were all on the same line. All right? If we think about our 3 points forming a triangle, but the 3 points happen to be on the same line, what would be the area of the triangle that's formed? 0, right? It's a triangle with no, who said 0? Did you say that, Sean? All right. So it's a triangle with no width or depth or whatever you want to say to it.
And
So
by the same line, you mean like all the y's or like all the x's?
I mean all the points,
Oh,
right?
yeah.
So if I put these points and it turned out that my 3 points, if I had a point anywhere else, I could form a triangle from it.
Yeah.
But if they happen to be right here, I can't form a triangle. So my area is going to be 0. And so you can, because of that, you can do the same process here. But if you assume that the area is 0, it's a way to test and see if the 3 points that are given are on the same line. All right. So you can. This is the test for collinear points, and it says. Test for collinear points. Again, we have 3 points, just like before: x1, y1, x2, y2, and x3, y3. These points are collinear. In other words, they exist, they are on the same line. If and only if we build the same matrix that we did before, taking the determinant of that matrix, and if they're collinear, then this determinant here has to equal 0. So I know we're butting up right against lunch here, but I do think it would be helpful to just one more time give you some practice on this. So they give us these 3 points, and the points this time are -2, -2, 1, 1, and 7, 5. And so they ask us, are these points collinear? So what we do is we build a 3 by 3 matrix using these points. We use all of our x values, -2, 1, 7, all of our y values, -2, 1, 5. Right? Here there's no easy choice because we don't have a 0 anywhere. Right? So we're just going to pick one of them. Do you guys want to pick a particular one?
1, 1,
Yeah.
1.
Think of that middle row there,
Middle.
right, with the 1s in it. So we're gonna look at A. We're gonna look at A21, A22, which is also equal to 1, and then A23, which is 1. All right, so we find M first. So if we think about that in our minds, if we cross this out, the resulting matrix is going to be a matrix that is, I'll just write it down so we won't lose track of what we're working with here. Does everybody agree with that's what the matrix looks like? Let me put it up above it, actually. 8, 2, 7, 1, 1. We'll just go ahead and do that for each of these guys. If I cross out, so that's if I crossed out this. I did that wrong. You guys didn't catch me. I trusted you. Right?
Worst mistake you ever made.
They're like, I'm just thinking about food. All right, let me just, we'll set it up and we won't actually solve it. But I'm focusing on this. So I cross this out and I cross this out.
-2, 1, 1.
-2, 1, 5, 1. Right?
Yeah.
All right. And so my next one, I'm going to cross this out and this out. So that's the matrix that I wrote down. -2, 7, 1, 1. And then for this third one here, cross out this and this, so -2, -2,
7, and 5.
7, and 5. Okay. So we find out, I'll do 1, we find out M21 is equal to -2 times 1 is -2 minus 5, so that's going to be -7. And since it's right here, what's the sign going to be, dude?
It's going to change.
It's going to flip, right? So C21 is going to equal +7. So we could go through and we could do all of those, and what we would find out from this one here, if we did everything correctly, is that we actually get a value of -6, and we would have proven that these points are not on the same line. They're not. Okay? So I'll let you do that in your homework. You can practice that. A lot of stuff today, a lot of places, like I said, to make mistakes. So make sure if you have these on a quiz or on a test, that you guys show me your work, that I can follow your train of thought, right? So that I can give you partial credit. Don't just write down the answer, and I'm left guessing whether or not you did what you did. Okay? Sound good?
Uh-huh.
All right. You guys have a good day.
Right.